So when we are looking at binomial data with a high or low probability of success. Now I'm going to write it out for the low probability case because this is how it's usually discussed. If you have a high probability of success, you can just flip it around. If I say there's a 99% chance of success, then I'm saying there's a 1% chance of failure. And so when you're close to 100%, you should just consider the failure case, and that will put you in the setting we're looking at here. 99% becomes 1% failure chance. So binomial random variable with a very low probability of success. In other words, p is small. Then there is a result using something called the Poisson distribution that will tell us that our binomial data can be approximated using a simpler distribution. So let me define that distribution first. So a random variable x has a Poisson distribution if the PDF is the following. So probability that x equals k is given by this. And we're counting the number of successes. So the number of successes in a binomial is an integer. So it could be 0, 1, 2, or so on. Now, what does lambda mean? Lambda is a positive constant. Lambda is called the success rate or the rate. And we'll see that with binomial data, it has a specific value. Now let me add a little note here. When we're looking at a Poisson distribution, the expected value is lambda, and the variance is also lambda. So that's a little bit surprising that both of them are the same in this case. So if you look in the book, they will demonstrate that this is a PDF, meaning, well, we can check that it's always positive. E to the x is positive, lambda is positive, factorials are positive. So we have a positive value. And the only thing that needs to be checked is that they add up to 1. So you can look in the book if you want to see it. It's not terribly difficult. It just uses a binomial sum. So this adds up to 100%. That confirms things. Now, the E of x and the variance statements can be checked using material we've learned before. Yeah, what's the question? It says there was a hand raised. Here we go, chat box. I don't hear anything. Let me check my audio then. So he's talking? My audio appears to be working. Oh, okay. Okay, so Devin, it sounds like you don't hear us and we don't hear you.
Hello?
Yeah, okay.
Can you hear me?
Yeah, now I can.
Oh, perfect. Thank you. All right. Sorry about that. What was I gonna say? Oh yeah. So that PDF function you have right there, is that the Poisson distribution, or is that just like a factor that makes something like an attribute of something that has a Poisson distribution?
No, this is the definition of a Poisson distribution. So
Okay.
if you have something of this form, you call it a Poisson distribution.
Okay.
Yeah, so at the moment, it doesn't seem like there's any reason to look at it, but we'll find out in a minute that the binomial follows this pattern. And yeah, so the expectation can be calculated using the definition. You just take a summation with k times this, and not very pleasant. And the variance, a similar thing with k squared times this, and that's an even more unpleasant sum. But they can both be calculated, and you'll see that this note holds. Now, the book gives some examples of Poisson distributions. I find it more helpful to learn the binomial application and then sort of work backwards. Because the reason why their examples work is a consequence of the binomial case. So if we have binomial data, so if we are looking at binomial data, it turns out that the rate lambda is just n times p. I'm trying to find where they state this in the book. It's in here somewhere. There we go, Poisson limit. Actually, I presented it out of order. That's the reason why I thought theirs seemed a little strange. Okay, so there's our definition of Poisson distribution. And now let me give you that connection to binomials. So if we have a binomial random variable, as was stated at the top, then it follows a Poisson distribution if n is large and np is basically a constant. So it follows the Poisson distribution with lambda equals np if n is large and lambda is basically a constant. And I'll put this in quotes for a reason. So if you look in the book, this is theorem 4.2.1. And they don't state it in quite the same way. They talk about limits. So they take the limit as n goes to infinity. So that's certainly large. And then they take p goes to 0. Now those conditions aren't quite useful because we don't have infinitely large data sets and we don't have probabilities asymptotically going to 0. So the theorem gives us the limiting behavior, what would happen if you keep getting bigger and bigger and bigger and smaller chances of success. And asymptotic behavior tells you what happens when you're kind of close to the limiting conditions. So kind of close to infinity is just saying a big sample. P kind of close to 0 is saying that product, NP, should be a small constant, a small number. That's somewhat vague, but roughly speaking, if n is more than 100 and lambda is less than 1, then you're probably doing okay. If n is much bigger than 100, it's going to be even better. And if lambda is much smaller than 1, that's even better too. If lambda is a small constant, like 2 or 3, instead of less than 1, it will still work, but the accuracy won't be as good. So typically, n should be more than 100. And if lambda is less than 1, then it is more accurate. So pretty good. If lambda is between 1 to 10, and again, these are very vague statements, then it's going to be okay. And if it goes beyond that, it's probably not going to be very good. But these are all very vague because if n was 10 billion and np was 11, then p is still really, really small. Now, just in the sort of data we look at, this sort of rough idea works. But if n is getting big enough, it can make up for this lambda value being larger. Okay, so why don't we give this a try? So let me write the formulas down in the corner here. So you have lambda is np, and then the probability that x equals k, or the PDF, should be roughly e to the minus lambda, lambda to the k over k factorial. And this was if n is large and np is small. And being aware that these are intentionally vague statements. Okay, so let's take that airplane example. let's say that 200 tickets are sold for a flight. And previously I said 95% of passengers will make their flight. But in this case, we need small probabilities. So let's say 5% will miss their flight. And let's estimate. Let's say the probability that fewer than 5 passengers miss their flight. So this would be like saying more than 195 showed up. So if our plane could hold 195 passengers, this is the chance that too many show up. Now we can find this exactly with binomial, and then we can find it with Poisson. So first let's do binomial, which is exact. And then I'll do the Poisson afterwards for comparison, and also to see how these sort of vague thresholds play into the accuracy. So we've seen this one before, the binomial distribution is n choose k, p to the k, 1 minus p to the n minus k. Here we have 200 tickets and a 5% chance of missing. The question says the probability fewer than 5 miss the flight. So that's the probability less than 5 successes, where in this case, success means they miss the flight, which I guess is successful for the airline and not for the passenger. So we've done a few problems now where you had intervals or ranges with binomial. And how do we handle something like this? The formula does not tell us a range, it tells us a specific number. Yeah, Derek?
You do the summation?
Correct, yeah. So we'll add up the cases that are less than 5, which would be 0 to 4. 200 choose k, 0.05 to the k. And I think that number kind of blurred there. Now we've done this on Wolfram Alpha a few times, but let me switch back to it anyways, because you'll need this again on the homework, and you want to make sure everyone's familiar with it. So the way to calculate something like this is we just type sum of 200 choose k. So I'm basically writing down exactly what that formula was. 0.05 to the k, 1 minus 0.05, and you could certainly put 0.95 instead. Here k went from 0 to 4. And that's 0.0264. So there is about a 2.6% or about a 1 in 40 chance that fewer than 5 passengers miss the flight, which, as was discussed before, means if you're the airline and you have 195 seats, you should sell some extra tickets and pocket the money from the no-shows. So now I'll switch back to the whiteboard. Just waiting here for it to connect. There we go. Okay, so that was our binomial answer. And now let's do this again, but use Poisson. So Poisson is an approximation because the theorem about Poisson is a statement about limits. We don't have infinitely many passengers, we have 200. So it's, again, approximation. So n was 200 again. P is 0.05. So the rate lambda is 200 times 0.05, which is 10. So looking at the conditions I wrote in the upper left corner, and previously I said large should mean something like more than 100, and lambda small should mean something like a small integer. I use 10 as a cutoff, like less than 10. So in this particular case, lambda is 10, so it's getting kind of towards the limits of where Poisson is going to work well. So we should expect that the answer is in the rough ballpark, but it would be surprising if, say, the third decimal was correct. If lambda were much smaller, like 1 or 2, then we would expect a pretty good approximation. So maybe if it was around Christmas time and the no-show rate is much smaller, then the Poisson approximation would be pretty good. Okay, so let's see, there's a formula at the top. So the PDF that we're working with here is e to the minus lambda, lambda to the k over k factorial. So e to the minus 10, and then 10 to the k. And let me calculate a few of the numbers here. So probability that no one misses the flight, probability one person misses. So nobody misses would be e to the minus 10, 10 to the 0 over 0 factorial. 0 factorial is 1. So this is really just e to the minus 10. E to the minus 10 is really small. So 0 point, and then you have 4 zeros. 4, 5. Then I'll do the case with 1. This will be e to the minus 10, 10 to the 1 over 1 factorial. That will be oops, I typed e to the minus 1 in. 0.000454. There's not a lot of numbers to do here, so let's just do them all. Probability of 2, 3, 4. Okay, so for 2, I will be multiplying by 10 squared over 2 factorial. I had more decimal places of accuracy last time, but it's getting out far enough. And then 10 cubed over 3 factorial. And then 10 to the 4th. And those are the 5 possible cases where we have fewer than 5 people miss their flight. So now I can add them all up. So adding them all up, there's that first term is really, really small. and keep on going like that until we get the last one there, 0.01892. I'll type them all in to my calculator and see what I get. Give me a minute for that. And this will be 0.029. So that wasn't bad. It was pretty close, but like I stated earlier, having lambda equals 10 was really towards the limits of where this is accurate. And so it was reasonably close, but my prediction that the third decimal place would be wrong was correct. So it's off by a relatively small amount, about 10% error. If our lambda value had been much smaller, this would have been much better. But it did, again, give a pretty good ballpark. In contrast, when we tried to use this with the continuity correction, it was very wrong. By a strange twist of fate, when I did it without continuity correction, it actually gave a very good estimate with normal distribution. But that was, in a sense, bad luck because it shouldn't have done that. So Poisson was pretty accurate. Normal distribution with continuity correction was very bad. Yes, Devin?
So if you had a larger sample space, it would be less accurate of an approximation because lambda would go up. Right, because if lambda is sample space times the probability.
Sort of, yeah. I mean, I see what you're pointing out, that when you get a larger sample, things should get better, right?
No, things will get worse.
No, but they should get better.
They should get better.
Yeah,
that's what I would think.
Yeah. So we only use this when we look at relatively small totals. Like here, the total was less than 5.
Mm-hmm.
And if n is getting really large, then, and I'm still looking at the chance of less than 5 no-shows, then the error will go up because the Poisson will be much larger than it should be. It will basically be minute, but not as minute as it should be.
Gotcha.
So yeah, in order to fit kind of what you're saying, I would need my cutoff instead of 5 to keep going up. Like here, 5 no-shows was half of the expected value. So if I had 1 million people I was looking at instead of 200, then 5% of that would be 50,000. And so the equivalent to this with 1 million people would be looking at 25,000 no-shows. And that's really big. So we wouldn't use Poisson with large numbers like that.
Okay, thank you.
E to the minus lambda offset the increased sample size. Yes, it does make an adjustment. Really, we shouldn't use Poisson when we're dealing with large numbers. I mean, large X values. So if we wanted to, I could even throw another condition in at the top and say X is less than 10. But just like all of these rough heuristics, it's not a perfect claim. Okay, let's look at another example with Poisson. So this is taken from an exercise in the book. This is looking at a medical study and mistakes being made in prescriptions. So a medical study has 289,411 prescriptions written. And 905 of them had mistakes. And the question we're being asked is, if a patient has 10 different prescriptions, then what is the probability there will be at least one error? And let's do this with Poisson, and then I'll follow it up with the correct binomial answer. And I will mention, if you're looking at this, you're going to find the binomial answer is not that hard, and so it actually feels like Poisson is a waste. And I'll explain in the next screen why Poisson is still relevant in cases where we might be looking at something like only one error. Okay, so we'll start with Poisson. Here, N, 289,411. P is the probability of success, which in this case refers to mistaken prescriptions. So how would I find the value of P, the probability of a mistake in a prescription?
Professor,
Yeah.
real quick, it's not a big cutoff, but there's a little bit of cutoff on the side. So
Awesome.
Can't really see the E of EX. Oh yeah, perfect.
Oh, whoops, wait a second, now I'm totally confused. Something's happening weird on my screen here. Is it moving around?
Yeah, now it is. We can kind of see it stuttering around.
Okay, what happened is so what, do you only see my whiteboard or do you see other stuff too?
Just the whiteboard.
Okay. I thought I had just moved the whiteboard off to the corner of my PC so that I could see my calculator, but it sounds like you're telling me that it had moved it off on your screen as well?
Yeah, it was just slightly moved over to the side a little bit.
Okay, weird.
But we
Okay,
could
I'll
only
just make
see
sure
your
I don't do
whiteboard.
that again. I thought, like I said, I thought I was just moving what Zoom showed me and not what Zoom showed you. Okay, sorry about that. Was some material cut off on earlier slides as well then?
No, I would have mentioned it.
Okay. Yeah, if it ever looks like something I'm writing isn't showing up, let me know. This was a new one for me. Like I said, I didn't realize that what Zoom tells me here seeing may not actually be correct. Okay, so I need the probability of success. How would I find the probability of success? Meaning the probability that a prescription is an error.
Do 905 divided by 289, 411.
Okay. So 905, 289, 411. So that's 0.00313. So that is certainly small. So Poisson needs n big. I used as a rough idea more than 100. This certainly fits that. And then the other part was lambda equals NP. If I multiply these two numbers together, I get 289,411. A large value. Oh, okay. This looks wrong. There's a reason. So let's take that away for a second and try to think about what we're trying to look at here. So this says the patient has 10 different prescriptions. So what we're looking at here is not quite what it seems that we're looking at here. It doesn't tell us that we're taking a sample size of 289,000. We're actually taking a sample of size 10. Right, because the patient comes along with only 10 prescriptions. So the 289,000 was just used to calculate P, the probability of success. Now we have n equals 10. N equals 10 does not fit the idea that it should be more than 100. So this may be a matter of concern, but lambda is going to be small. So it's a very small lambda, but the sample size is possibly not large enough. So we'll go through and do the calculation and see how well it works out. So that's too small, but that's good. So our Poisson probability we're supposed to find the probability that x is at least 1. Does anybody have a suggestion for how we can calculate this? Yeah, there's a hand raised.
Do 1 minus px equals 0.
Correct. Yeah, so you could add from 1 to 10, but it is a lot easier to just look at 0. And the whole point of using Poisson is usually that we want to have simpler calculations. It's even with computers, we actually still want methods like this, because when we're looking at something that involves something like half-life of a compound, you may have a huge number of atoms and a relatively small decay rate. When you have this Poisson formula, you can solve problems with it, whereas you can't really do problem solving using binomial formula. You can use a computer to calculate specific cases, but not to algebraically solve something. It looks like hand raised still.
So it says patient has 10 prescriptions, so n equals 10.
Right.
And then it says it's too small.
Because I had suggested that we usually want 100 or so.
So why would lambda equals np? What do you mean when you say good?
Well, we want lambda to be a small number, definitely less than 10 if possible, and less than 1 is even better.
Oh, right. So
there's a bit of a trade-off here. The lambda value is so small that it's way below the recommended threshold, which is a good thing. But the sample size should be larger. And so there's some question of whether or not this is going to come up with a good answer, given our sample size is small, but our lambdas may compensate for that.
So if the ratio between lambda and n is similar to like what would be considered a favorable outcome, or like the favorable range that we defined earlier, can you still use it?
Generally speaking, what's most important is that lambda is small.
Okay.
So if I would expect that the answer on this will be decent, but I couldn't say without computing numbers whether the small sample size will end up playing a significant role. Just like if lambda was bigger than 10, but the sample size was really huge, that may be fine as well. You know, anytime you have these limits, there's not clear answers. There's just sort of rough ideas of what seems to work. Okay, so lambda x equals 0. We have 1 minus, now e to the minus lambda. And then lambda to the 0. over 0 factorial. So I'll plug that in. And I get 0.031. So that's the Poisson answer. And then we'll use the binomial to find out if this was good. So we're still solving the same question, so we can still just say x is at least 1. And what changes is that instead of that Poisson approximation, I'll be taking n choose k and so on. What is the exponent in the last part? Okay, let me erase the little mistake I made instead of just trying to write over it. So that was 313 to the 0th power. Okay, so this will be n choose k. Here n was only 10. P to the k. One minus p to the n minus k. So that's the probability of having 0 prescription mistakes. And now I will type this in to a calculator and we'll see what we get. This will be 0.03. In fact, I should have written more decimals on the first one, because this answer was so good that, well, actually, I'm going to leave the 1 there, and then we're going to actually need to use all the numbers need more precision if I want to compare more decimals. So this is 0.03086. So basically 0.031. Let me fix the answer to number 1 to have more decimal places of accuracy, just for comparison. So if I had wanted to improve this and make it even better, I type this in where I didn't do any rounding until the final answer, and I get 0.03079. So these two answers are quite close. So that shows us that even though our sample size n was pretty small, the value of lambda was so small that it managed to make up for it. So about a 3% chance that our patient has an error. Are there any questions about this? Okay, so I said that now we're going to look at a Poisson example where we might be able to answer the question even if we're missing some data. So this is going to be one of those situations where, as I said, even though the binomial formula can be plugged into Wolfram alpha, there may be problems where we can't use it. And we can use Poisson. So let's give an example. So let's say that we're looking at a major hospital, so a large hospital. Admits an average of 2 babies per day to the NICU, neonatal intensive care. What is the probability more than 10 babies go to NICU this week? Actually, I'm going to change this to a simpler one for now. More than 5 babies are admitted to NICU in a single day. So if we look at this question, it doesn't even look like it's binomial. I've said there's an average of 2 babies a day that go to neonatal intensive care. And I want to know what happens if there are, or what's the chance of 5 babies or more being admitted. I guess I said more than, I meant 5 or more, but I'll leave it how it is. And just looking at this, there's no way to answer the question. So we need to think a little bit about the context here. So if this is a large hospital, that means there are many babies born every day. So that's like saying we have a large sample size. I haven't told you what P is. But we have been told 2 babies are admitted to NICU. So the rate is the product of the number of babies born times the percentage that go to intensive care. We don't know how many babies are born in this hospital, and we don't know what percentage of them are admitted to intensive care, but we do know the rate lambda. And the Poisson formula lets us answer questions about this type of setting as long as we know lambda. So don't know P, don't know N, but we do know the rate. So Poisson can be used. So the Poisson formula, as we've seen a few times, will be e to the minus lambda, lambda to the k over k factorial. Lambda was 2. And then I need to add this up from 0 to 5 in order to answer the question. So probability x is greater than 5, just like on the previous one. we can take less than or equal. And I'll do this on Wolfram, so I'll switch over to that in a moment. So this was our last question, but here we'll do, so 1 minus the sum of, in the formula we looked at, e to the minus 2 times 2 to the k over k factorial, and k was 0 to 4. Now I'm not sure whether the 4 part will directly apply to the sum or somehow apply to the 1 minus. So just to be safe, I'll stick some parentheses in there so that there's no confusion. I don't think there would be anyways, but it's always good to make sure. And they do give us a picture of what our math is. So that's another way to double check that you have the right sum. So it tells us about a 5% chance. (0.05). Wait a minute while I switch back to the tablet. Okay, so we were able to determine whether or not a large number of babies would be admitted to the intensive care unit without knowing probability or sample size, just knowing how many happen each day. So this is a very useful application of Poisson, because as long as we know that our data set involves a large number of independent samples with a small probability of something occurring, then the approximation works, even though we don't know the other numbers involved. I'm going to give one more use of this data to show another way that we can answer things nicely with Poisson. Now I just shrunk things and moved it to the corner on my screen. Can you see everything that was there before? It should just be sort of in the left-hand half.
Yes.
Okay, I just worried after having things cut off before. So I guess that as long as I show my zoom window in the middle of my screen, we see the same thing. And my mistake was when I tried to push it off on the side to look at a calculator that I had trouble. Okay, so what I'm going to do here is revisit this problem. Oh, by the way, why would we want an answer to this? So the intensive care has a limited capacity. And if the hospital thinks there's a decent chance that they're going to have, I didn't even answer the right question. I wrote less than or equal to 4. If the hospital thinks there is a decent chance, I'll fix these numbers in a moment, that there are going to be too many admissions, then they need to have contingency plans. So they certainly don't want to say, your baby needs a ventilator, but tough luck. So if the chance that they're going to have more than 5 babies is high, they need to have a way of dealing with that unexpected surge. So maybe that means that they add extra capacity that they don't really need. Maybe it means that they have a sharing arrangement with another hospital to transfer babies. But whatever the case may be, they don't want to have a case where a baby is born and needs urgent care and they have no capability of providing that. So let me just fix the number here to match with the question, because it wasn't doing that before. I'm going to type this up. I'm going to just change my 4 to a 5 on Wolfram, but I won't switch back over to that. So that became 0.016. Okay, so even smaller, 2%, 1 in 50 chance. So, but that does mean, so if there's a 1 in 50 chance, that means that every couple of months this will happen once. So if the hospital is only capable of taking 5 babies a day, then they do need to have a way of covering this rare event that happens every couple months. Okay, so I said that I want to do a modified version of this now. So let's suppose that babies are born at uniformly throughout the day, which is not true, but let's suppose that births occur uniformly throughout the day. Now, I don't mean that every hour has the same number of babies born. We're looking at random variables. It means that if I were to plot the distribution over time, maybe if I took 1 year of data, I would find that about 1 out of every 24 babies were born between 12 to 1 a.m. About 1 out of every 24 are born between 1 and 2, and so on. But on a specific day, it could be that I have a surge in the morning and very little in the afternoon. So specific days may not be divided up nicely. It's over the course of a long period, like a year, that this happens. So suppose births occur uniformly throughout the day. But we still need to worry about capacity. Having more than 5 babies admitted in a day could be a problem, but having too many babies submitted in a short period of time could also be a problem. So what is the probability that 2 or more babies NICU cases, let's say before 8 a.m. And that might be a situation where at the end of the day, the hospital checks that the intensive care is fully staffed for the number of babies they have and has just a little bit of extra capacity before the morning. And then you get a morning change of shift and maybe then they can deal with more. Now, my son was born at, I believe, around 2 a.m. in the morning and went straight to intensive care. So he would be one of these cases. He went to NICU just because he was born 5 weeks early, but actually he was a big baby and everything was happy, so that was good. His main side effect was young babies have a soft skull. So when he was a baby, the side of his skull got flattened from lying on his side and he had to wear a helmet for a while. So he was like a little crawling football player. Okay, so what's going on here? We only want to look at cases before 8 a.m. And we were not told the cases before 8 a.m. We were told 2 per day. So I'm going to rewrite that lambda as 1 day. And that's 2 cases. Before 8 a.m. is an 8-hour period. So how could I take the 1 day of data and get the rate of NICU cases in an 8-hour period? Any suggestions?
Divide by 3.
What was that?
I was thinking divide it by 3.
Yeah, exactly. So we just say 8 hours is a third of a day. So 8/24 for the rate for 1 day. So one third of that, so 2/3. So we expect to have about 2/3 of cases before 8 a.m., which means usually it'll be 0 to 1. But 2 is not ridiculous. Now we want probability the number is greater than or equal to 2, keeping in mind that x in this new version is not the same as x in the old one. Previously, it was a 1 day answer. Now it's an 8-hour answer. That will be 1 minus the probability it's less than 2. And I can take the same approach I took before of adding up a sum. This is small enough that I don't really need to use summation notation, but I'll do it anyway. So e to the minus lambda times lambda to the k over k factorial. With only two values, you're probably better off just typing them in. So I'll just write them down here. So I'll type them into Wolfram and give you the answers, but not switch screens back and forth. So the zero case is 0.51. That means that about 50% of the time, there should be no NICU cases before 8 a.m. And then for one case, that's 0.342. So half the time there should be no cases. A third of the time there should be one. And then we can plug that in. The chance that there were two or more cases. One minus 0.51 plus 0.34. That will be about 15%. Now that's a reasonably high fraction. In terms of ratios, that's about 1 in 6. So every week there should be a day where this happens. So they definitely need a contingency plan to staff the NICU a little more. And given the significance of not having babies die in your hospital, that means that the NICU will probably be staffed for more than 2 new babies in all cases. Because a 1 in 6, if this happens every single week, they don't want to be having a crisis every single week. So are there any questions about what we just did? Okay, so this is covering what we're going to do for Poisson. Now, if you do look at the textbook, they have somewhat different approaches to studying this. So they have some different formulas that they give, say in the case that we just did here. However, I think it is easier to handle these problems by simply adjusting the rate of lambda as I did in this question. So when you go to do the homework, if you look at a problem that involves time, for example, you can take the approach the book uses. But again, I think you will find it easier to simply adjust your rate rather than taking their approach. So let's take a break for 10 minutes now. And then after that, we'll come back and we'll finish out chapter 4 with a couple of other special distributions.